So if we have our ball bouncing here, and the starting point is 100 meters, and every time we're taking 3/4 of that. So then it's 75. Okay, the height after the first bounce is 75. That's the height after the second bounce. That's the height after the third bounce. How many bounces do you think it made when we actually dropped it before it kind of stopped? How many did it seem like it made? You want to count them? Let's pause this and we'll count them. We start with 100. We multiply it by 0.75. This is a model for what's happening in reality. In our model, does it ever stop? No, it doesn't, right? What's going to happen here? Like I'm up to 20 probably by now, whether it was 18 or 20 or however many bounces you thought happened. In our model, is it ever stopping bouncing? No, it's not, right? The model we're using, it's bouncing forever. At this point, how high is it bouncing? Like this 1 times 10 to the negative 5? That's kind of negligible how high it's bouncing. You couldn't even see it on the picture that I drew. We're using a sequence to model this that doesn't end. Okay? If we go back to this picture here, if we say we're going to start with 100, then 56.25, then whatever, and we just let it keep going, in reality it stops bouncing, but here this sequence is never going to stop. There's no end to it. This is called an infinite geometric sequence, or series if we want the sum. Okay, infinite geometric series. You guys had a hard time counting how many bounces there were. If we want to know how much vertical distance it travels before it stops, which is what we're going to do kind of at the end of this here. If we want to know how much vertical distance this covers, like it goes down, then up, then down, then up, then down. If we want to know all of this that it does before it comes to rest, instead of trying to say how many bounces does it make and use that, like, do we do the sum of the first 20 terms? Do we do the sum of the first 18 terms? How many bounces were there? I don't know. What we're going to do is we're going to say, as you go on, what's happening to the heights here? They're getting smaller and smaller. At some point, they're so small we can't even draw them anymore, right? If you go back to the calculator here, by the time I'm here, how small is that number? It's like 0.00000179. This is basically nothing compared to what we started with, right? If I take 100, if I start adding these up, let's think about what I've got here. Let's roughly estimate this. After 2, I've got 175. After 3, I've got, 230 or something like that, roughly. Then maybe I have about 270. Then maybe I've got about 300. Every time I bounce it bounces again. I'm adding less and less on. By the time you get to 20 bounces or 22 bounces, each one is basically nothing. You're adding less than 0.0, you're adding this much on. If I take a number like 300 and add 0.000001 on, how much do I have roughly? I still have roughly 300. They factor in less and less as you go on here. So we're going to model things with what you call infinite geometric series. Okay? We're going to model the ball bouncing question with an infinite geometric series. This is a silly example here, but we'll use it anyways. Okay, an infinite series. Before we start thinking of this, an infinite geometric series means it's going on infinitely. It's going on forever. There's dots at the end, right? If you look back up here, I wrote the first few terms and then put ... It's going on forever here. If we just keep doing 3/4 of something, it's never going to end. But you can see in reality, there is kind of a finite amount of distance that the thing travels. This is maybe going to be easier for you to see here. Let's pretend that you decide you're going to eat a pizza like this. if you read that. Let's draw the pizza. Well, we're just going to make a circle and pretend it's a pizza. Okay, you're going to eat it this way. Here's how you're going to eat it. You're going to eat half of it. Then you're going to eat the half of what's left. Then you're going to eat half of what's left. Okay? This reminds me of when I was a little kid and my mom had these candies in the cupboard for baking something or other, cookies or whatever, and I thought, oh, there's this big bag. I'll just sneak in there and eat some of them, right? So pretend I ate half because she's never going to know. Some of them are gone, so I eat half of them. And then a few days later, oh, well, look, there's this many. I'll take half of what's left there because she'll never notice. I didn't say half, but it eats some, right? But eventually I get down to the point where, oh, look, there's only one candy left, and I eat that one and it's all gone, right? In this situation, there's always going to be something left. Okay? My mom figured it out, by the way. She had more wisdom than a 4-year-old or 5-year-old or whatever. Suddenly all the candies are gone. There's a whole bag there before. But if you just take a little bit at a time here, if you eat half the pizza, you still have half the pizza left. And then you eat half of what's there. And then you eat half of what's left there to eat. And you eat half again. If you keep doing this, okay, you eat half of that. Lines are getting pretty thin here. This is probably not going to work very well, but, eat half of that. If I keep going with this, it's hard to draw. First I ate a half of it, then I ate a quarter, then I ate an eighth and a 16th and a 32nd. Then I'm eating a 64th of a pizza. You don't often divide your pizza up into 64 pieces or 128 pieces. In theory, would I ever finish? In theory, I would never finish, theoretically. I know in reality we'd get down to where the pieces are so small that there's only one pizza molecule left or whatever. Which, there's no pizza molecules, but whatever it is. And then you have to eat that one, right? But in theory, you're always going to have some left, right? If you always take half of what's there. So in theory, you're never going to finish. But if you look at the picture, by the end of it, how much have you eaten? If this went on infinitely, what does this add up to? How much pizza have you eaten? How much pizza have you eaten? One pizza, right? If you let it go infinitely, if we stop at any point, you haven't eaten a whole pizza. But if you let it go infinitely, you've eaten one pizza. So this sequence here, this series, even though it goes on infinitely, see dot, dot, dot at the end, what does it add up to? It adds up to 1. We're going to make this 1 a different color, and we're going to make it a large 1 here, because it's an important concept here. This is a hard concept. A series that goes on infinitely, there's an infinite number of terms in this sequence. I could keep writing them 1 over 256, 1 over 512, 1 over 1024. You could keep writing these terms infinitely. But it has a finite sum. What does it mean to have a finite sum? What does the word finite mean? Not infinite, exactly, right? Finite means not infinite. We have a finite amount of energy with which to study this course. You will run out of steam at some point. You don't have an infinite amount of energy. My 6-year-old has an infinite amount of energy. Okay, that's a hard thing to get your head around, is something that has an infinite number of terms has a sum that's not infinite. If I said I'm going to take an infinite amount of numbers and add them together, what would you guess? What would you probably guess that it adds up to? Infinity, probably, right? If I said I'm going to take an infinite number of things and add them together, your guess would probably be, well, it'll add up to infinity. If I took numbers like this and did that, then that might be the case. Okay? So I'll let you, while I stop this, I'll let you think about that for a second. Think about this question. I'm going to